Good day, and you're almost welcome to today's technical presentation of the CNPS. My name is Ian Cowan, and today is the 11th of October, 2025. Now, today we're very happy to have Frédéric Lassiaille back again to talk to us. He has talked to us on a number of occasions about some fascinating ideas he has, and well, today's talk, which has been advertised, is that his contention is that relativity predicts a variable g, which is the gravitational constant in Newton's law, the large G, the capital G. And he's going to focus on the mathematical details of the demonstration that is so. So, excuse me. The genesis of this was that on previous occasions, Frédéric was good enough to give us talks. Last October and last January, actually, he gave us talks on this concept of G, the gravitational constant, being variable. And in fact, more recently, in August, that has just gone by, he gave us a talk on his theories involving surrounding, as distinct from the common views which are expressed now of dark matter and the question of modification of Newton's laws. Now, in the discussion, I seem to recall that people were asking, I think maybe I myself asked Frédéric, well, you know, how did you derive that? Maybe we wouldn't be shy from hearing a little more about the mathematical details as to how you come to the conclusion that a variable G is actually required by relativity. So that's the subject of today's talk. He's offered actually to come back and go into a bit more quantitative detail, as far as I understand it, as to how relativity predicts a variable G, and he'll tell you himself as to what he means by relativity, whether he's restricting himself to Einsteinian or whether it's a more general point. So, as usual, I'm just checking now. We have social media people coming in, which is excellent. They're very welcome. And we have people in the green room as well. we normally have 10 spaces, and that probably includes Frédéric's slides, which we have here. But we, in recent weeks, have not overloaded the system, so we have a couple of spaces still left. Okay, and then as usual, people feel free to post questions or discussion. There is a danger that unless it's very specific, that you're addressing a question to Frédéric, I may just consider it as conversation between people here. So if you have any specific question which you want the lecturer to address after his talk, please do say this is a specific question for Frédéric. And again, people in the green room will be invited to go into a bit more depth, maybe discuss some of the aspects, maybe contrast some of the aspects or compare some of the aspects with their own theories and so on. So we're looking forward to that. Right now, Frédéric, you're up, and I think I can say good afternoon to you because you're in the same time zone as me, whereas most people participating in the morning. But you're very welcome. Thank you very much for coming back to us so soon as well. It's not long
ago. Thank you very much, Jan.
So what I'm going to do, we had a very brief rehearsal for about a minute or two because I think everything has worked in the past, and you're a dab hand at it, and it should work perfectly. But do tell me if you want to bring down the slides, bring up your photograph, if you want to point to anything, and so on and so forth. So for the moment, what I'll do, Frédéric, is I'm going to move myself away, which means I'm not visible, I'm not audible. The screen will be totally yours if you want to speak for a moment or two. And then if you want to tell me to bring up your slides and maybe minimize your photograph, I will do that. But I'm relying upon your instruction because I'll be really off the side, and I'll only come back in an emergency, if anybody really says, look, please stop the lecture and ask Frédéric what he means by that, I just don't understand, we will do that in extremis, but we'll try to give Frédéric uninterrupted presentation time, and then at the end we'll address all these questions. So Frédéric, the floor is all yours now.
Thank you very much, Ian, and thank you very much for the CNPS organization for giving me the opportunity to present my work. So my name is Frédéric Lassiaille. I am an independent theoretical researcher. This has been for 20 years or so. And I would like to introduce my presentation of today by this very simple image behind me. Can you see it? Here. So you can see there is one man alone in the desert.
Yes, we see it perfectly.
Thank you. And the idea here is that as I will talk about relativity from the mathematical point of view of relativity. So we are not talking about this kind of physics interpretation of relativity or another one, Einstein or another. It's only the mathematical framework. In the mathematical framework of relativity, when you have an empty universe, like the desert here, it's empty people. Now, if you insert only one person, you can see it's quite weird, in fact. So let's start with that idea. I close this idea and I start the presentation. So maybe can you see the presentation? I hope it will work. Normally it should be full screen. I hope you can see it. Maybe Jan, can you confirm this is okay? So this is the first slide of the presentation. It is entitled Relativity Predicts a Variable Gravitational Constant, as Jan said to you. So I'll call it G, capital G. And it's only today talking about the mathematical demonstration. It's not so complicated. It's not. I will try to make it simple and short, if possible, and as much as possible, and also geometrical, because in mathematics there are very oftenly two different views of the things, which are algebra and geometry. And today we'll try to focus on the geometrical aspect because this one is much more interesting, funny and easy and funny to understand. So let's go further. So once again, a small funny remark. Earth is flat. That's something we heard today. We are hearing that today. We heard that long ago, many centuries ago. I don't know exactly the year. After that, we heard in the history of physics, we heard that the Earth was in the middle of everything, like here in this map. After that, we heard that no, it's the sun which is in the middle of the universe. And then today, it is commonly admitted that G is a constant value. Even though some fellows told us that maybe it could be wrong. Maybe this could be another anthropocentric mistake, G being a constant value. So that's why today a good idea would be to demonstrate that mathematically that G is a variable, and also if possible to calculate this variable. Therefore, the table of content of today is this: introduction, motivation, the real mathematical demonstration, and a quick look in the consequences, because they have been already addressed in the previous conferences here in his organization, the CNPS organization, the Chapel Natural Philosophy Society organization. The final picture and the conclusion. So the context. In the introduction, there is first of all the context. This work follows from previous works, which started more than 20 years ago. There was some publication, is a proceeding of some conference, an interesting, very much interesting conference in 2022. This was a very short introduction because it was 15 pages only. It's not enough for having a full demonstration, but it was a very, very nice for me. 15 pages presentation of this demonstration of today. And also, of course, the previous CNPS conferences. January this year, Relativity, Predicts Variability. It was more about my whole research work, in fact. And September last, only the gravitational model entitled Surrounding, which derives from this remark that relativity predicts a variable G. Today's presentation is only zooming on the mathematical demonstration proving that relativity predicts a variable G. So this is the whole research. So you got this blue block, which is the main part of it, which is really the center of it, from which everything is deduced. Even though the surrounding model is a gravitational model, which can be understood as completely as a standalone model, the surrounding model does not need this new relativity, this kind of new relativity, in fact, it's relativity, in order to exist. Surrounding is a standalone. Okay, so let's go further. So the motivation, the main motivation is, of course, as I said before, to solve the anthropocentric mistake, which is about the G constant, of course, but there are some more motivations which can be found, either general motivations or more physics, more motivations in the general relativity point of view. Okay, we will go back on those like caveats of general relativity. Let's go further. So today we are talking about this part of the research work. So once again, I show you this desert, which is illustrating what is going on with a particle which is alone in an empty universe. So maybe, please allow me to repeat again, an empty universe. So the idea here is to study the function in mathematics, which is a mathematical function, in the mathematical framework of relativity, this function being giving the space-time structure from energy. And here, the distribution, the energy distribution is extremely simple. We have an empty universe, like a desert here, for example, illustrating, and we have only in it, we inserted one particle in an empty universe, so one man only in a complete vacuum of people. So when you see that, when you just spell the word, in fact, you understand that the result can only be completely bowing. The space-time structure must be bowing in the direction of the only one particle, which is here, for example, represented in 1686. It represents the Siam ambassadors at the court of King Louis XIV in France. So there were people coming to see this guy. He was young at this time, apparently, very young. But they were bowing because he was only one with the power. He was the only one who was endorsing the role of power, of energy, if you like. Therefore, everybody around him just bow very deeply in front of him. Like this. bowing in the direction of the only one. So therefore, it seems the mathematical configuration here is that the consideration is that it seems intuitive that in this context, everything conforms to the presence of the particle. Sorry, there is a two here. The scenario is unrealistic also. It's quite the same kind of remark. The scenario is unrealistic. Why? Because you assume that the energy, the universe is empty. So therefore, this is completely unrealistic, isn't it? Once more, you imagine that you put only one particle in an empty universe. It's completely kind of foolish, in fact. Therefore, one should expect the calculation to yield only an unrealistic result. Those are only considerations on mathematical grounds, but there is also a mathematical demonstration. So I don't have the time to go into full detail of it because time is short. And also, the following presentation will show a much more constructed demonstration of the same thing. The result is that there is singularity throughout space-time. We will go back in more detail about what is this singularity. In fact, it reacts really like that, like bowing. Everybody is bowing in the direction of the only one particle. That's what we will see. So this is for the particle alone in a particular universe. So what happens for more than one particle? This is also what we will try to answer. And this is also why we need a much more constructed demonstration than the one I was showing you just a minute before. The principles now of the demonstrations are different. There are different kinds of principles. We try in this demonstration to find another equation than Einstein equation. Problem with, if I can say so, the thing is with Einstein equation is that it deals only with the second degree of derivation link. Here we try to find an equation with the first degree in derivation link, which is of course compatible in some way to the Einstein equation, because Einstein equation has been proven more or less to be quite good. Also, there is a duality between non-null vector and null vectors. We consider relativity as a pure mathematical framework, so we get away all the physical interpretation, and also we allow ourselves to compare different energy distribution. I would say different in universe. No, it's the same universe with the same kind of law, but it's different energy distribution. And you allow yourselves to assume that maybe you can add another particle in this energy distribution, or you can remove it. Of course, it will violate the principle of energy conservation, but it does not. This is not a problem for the mathematical framework and for the mathematical function, which gives space-time structure from an energy distribution. This is exactly this S function, which gives the space-time structure from energy, and also S is on your. It gets a mathematical property. It is that you can invert the limit and the function because it's uniformly continuous. So this is the full part, the full demonstration. 9 parts for the demonstration of relativity predicting a variable gravitational constant. So I don't go into full detail right now. We will, or maybe a glimpse. This is the most important part of the demonstration, the concept of rest frame, which is here generalized. The result here on the first step is that we obtain something which is quite like an ether, but it's not an ether. It's an absolute space-time, that's for sure. And this absolute space-time, I call it in fact GRF, generalized rest frames. It behaves in some particular manner, which helps us to demonstrate many things. Then, once this is done, we can study what I was showing you before, the famous desert, the emptiness with only one particle. Then we see what is going on sorry, this is the particle moving at the speed of light on a straight line. This is even more weird. So, okay, sorry. And then we get this trajectory of this particle moving at the speed of light in an empty universe, moving along a circular path. And then we study that. And then there is the limiting behavior of that. We get this circle going smaller and smaller. The circle tends to 0, so reduce tend to 0. And we study the limit. And then from that, we have the result I was talking about, a singularity all over throughout the space-time for a particle alone in a universe. And then we go further with several such particles in an empty universe. And then we calculate space-time structure in any situation, in any configuration, using a new equation, which is exactly the new equation that we were searching for, dealing with the first degree of derivation. Then for me to deduce the metric, then we recognize that there is a surrounding effect which arises in relativity. And also we get an equation for G in the most usual circumstances. So let's start with this, the most important part of it, which is the famous absolute spacetime. So absolute spacetime is not something new. It's not an ether. It's just something already existing in relativity. If you examine the twin paradox here, you can see that the frame of the twin who stay on the Earth is a privileged frame with respect to the frame on which stays the traveling twin. So therefore, it's not symmetric. It's not completely relativistic. There is not an exact. So relativity, there is an absolute spacetime. So the idea here is to generalize this idea of privileged frame here. So it starts by working on restricted relativity and the strange things of it. And if we add a thought experiment to the twin paradox, we obtain something interesting, which is that a particle in a universe deforms. There is a deformation locally generated by a particle locally, which is described by the boost, which is linked to the speed of the particle with respect of the old rest frames. So we have the concept of old rest frame and the new rest frame. The old rest frame is a frame, the generalized rest frame, which is existing in a universe without the particle. The new GRF is a rest frame which exists after the existence of this particle to the same energy distribution. So you have an energy distribution. There is an old rest frame. You add to it a particle. Another rest frame occurs, and the link between the old and the new rest frame is done by the boost, which is associated with the speed of the particle with respect to the old rest frame. This is what we again obtain by studying the twin paradox with this thought experiment. I will not have the time to go into the full detail of this thought experiment. And then after that, we just have to interpolate, to generalize very much this concept of rest frame. We have to interpolate this concept to the event of space-time in which there is nothing, in which there is vacuum. That is only an interpolation. The most important thing is the work with this rest frame. So you imagine that, as I said before, that you have a Minkowskian space-time structure, like illustrated here, like this: x, y space dimensions and ct time dimensions. And it's a Minkowskian flat space-time all over the universe. And there is an old an old set of rest frames all over the universe, which is exactly this frame here. The system of frame which is all identical to this one. And then you add to this universe this p particle moving at the v speed with respect to this frame. What happens? What happens is that the new system of race frame has been modified. How? It has been modified by a transformation of the old race frame here at the location of p by the new transforming into the new race frame, and this transformation is done by the boost associated with the v speed. So as you know, when I'm talking about a boost, a boost is the Lorentz transform in its simplest formulation, that is historical Lorentz transform, okay, the Einstein one if you want. So let's go further. Now, if you go faster, so if V tends to be equal to C, then the deformation become a singular space-time deformation. Now, that's what I was talking about. So this is the boost we were talking about. So this is the formulation of the boost. You know, the historical one, or Lorentz transform, as you know. And this one is deduced from the speed of the particle, or you can deduce it also from the form momentum, the same way. Because in the form momentum, you can deduce immediately, you can read even the speed. You read the speed of this particle with respect to the old frame. And then you get the boost, we transform the old race frame into the new one. That's what I was talking about. Now, since you got those nice properties, you feel the need, the requirement of generalizing this concept of race frames, because you want to have an absolute space-time everywhere. So in order to get that, you just have to interpolate this concept of race frames by interpolating. Okay, so you use a mechanism in general relativity which are very much well known. I don't go into the detail of that. The result is that you don't obtain an ether, which because an ether, for my definition personally, it is a medium made of matter. Here, it's not a medium made of matter, it's an absolute space-time. Of course, it's very much related to matter, as I said before. But it's not really this ether with this definition. But the other two concepts are very close. Now, let's go further in the second part. So now we will study a particle moving at the speed of light in an empty universe along a straight line trajectory. So here, the result is that this particle, as I said before, it deforms locally space-time, as I said, but also it generates a gravitational wave. At first, the gravitational wave here is exactly identical to the deformation itself of the particle. But as soon as the P trajectory deviates from its geodesic trajectory, then you can see a difference. Then the gravitational wave trajectory becomes different from the trajectory of P. So you have to know what is going on with the gravitational wave. The result is that, as I will show you, is that the gravitational wave propagates a deformation which is exactly this singular space-time deformation. This might appear weird, but this is demonstrated here. So I don't have time, once again, to go into full detail. Once again, this demonstration is based, or maybe I can do it for once, because it will illustrate the kind of demonstration we have with this new concept of GRF. Also, let's go further quickly. What is it, in fact? As usual, when you want to demonstrate something in this new framework, you consider a surfing particle. So it's funny, you see, so you are in Los Angeles and you have this Q particle surfing on the gravitational wave. At first, Q and P are exactly in the same location, moving at the same speed. Okay, so it means that Q is moving at the speed of light at the beginning. But as I said before, P maybe it will deviate its trajectory from the geodesic trajectory. It will go elsewhere. But Q will, it's a free-falling particle, so it has no choice. It will still follow the geodesic. But since Q has the speed of light from the beginning, relative to either the old or the new GRF, also, of course, I'm talking about the old or new GRF with respect to P, of course, as usual. Since Q has a speed equal to C, the speed of light, therefore, it always moves at this speed. This is for conservation of energy. This is also much more than that. It is about more than that. So it's always this speed. Therefore, the space-time deformation generated by Q with respect to the new GRF remains null. It is null because Q goes at the same speed as of P at the beginning. So with respect to the deformation of P, the deformation added by Q is null. You see? So because of this remark here, this deformation remains null all the time. And also, otherwise, its energy, the energy of Q, would become null. This is easy to prove. You have the famous Doppler effect. So because of the Doppler effect, the energy cannot be null. Because the energy, because of the Doppler effect, the energy would decrease very much if it were not true. So therefore, the space-time deformation stay null. At the same time, the space-time deformation now, with respect to the old GRF, is singular, of course, because without P, the space-time deformation generated by Q is a singular space-time deformation. It's a speed of light. Therefore, it's always the case. It is also always the same speed of light. The result is that the new GRF are given in a singular way, with a singular boost, with respect to the old. This is exactly what was claimed before. So it appears to be a very weird result, but you have to understand also that the space-time deformation we are talking here is an irreversible. It cannot be modified by energy outside, because the assumption here is that P is dimensionless, Q is dimensionless, for example. And that, for that reason, the result is a little bit weird. But once again, it's a model. It's a mathematical model. So this demonstration was interesting because it's always this same kind of demonstration we use here with this new framework of GRF and with the properties it has. So now we take the limit. Sorry. Before that, we take the same example, but we modify the trajectory of P. We get a circle trajectory. So therefore, the gravitational waves are like this. It turns around. Okay. So at the end of the day, very far from P, asymptotically, we say it's asymptotically, that is very far from, infinitely far from P, the envelope of the gravitational waves, which are generated at each turn of P, they look like this. They are real spheres, asymptotically, I insist. So therefore, this figure is wrong because I could not illustrate the huge sphere with an infinite radius, of course. But you have to imagine that those spheres are in the infinite, are very big. Now, this is the fourth step. We take the limit of this circle to 0. So we decrease the radius of the circle. What happens? The asymptotic sphere gets closer and closer. Closer and closer, and at the end of the process, you get the full space-time. The full space-time is full. The space-time is full of singular deformations. This is exactly the result we were claiming at the beginning of this presentation when we were talking about Louis XIV and the desert and all these things. And here, the demonstration also, I went very quickly. The demonstration uses the interchange of limits theorem. This is the A of n and I is representing the circle. It appears complicated, but it's very simple. It's simply the circles we were talking about. When we take the limit of those circles, we get only one particle, except that this one particle is made of other bunches of matter which are moving at the speed of light, along infinitely small circles trajectory. So this is here what I'm talking about. And then you take the space-time structure resulting. This space-time structure is exactly the limit of the space-time structure of each circle. It's exactly what we have been telling. The result is a singularity. Here it's already a singularity. The limit, when you take the limit, you get immediately the asymptotic spheres. That's why I was talking about the asymptotic sphere, because it is exactly what you get when you get the limit here. It's a asymptotic shape and the things you get when you get when you get the limit of the circle. Okay, what's space? Okay, this is the limit of the space-time. Okay, the result is this. It does not. So a particle alone in an empty universe does not yield the regular Schwarzschild metric we know about. We know from the literature, but it yields a singularity throughout space-time. Once again, we get this man. Or more precisely, we get this Boeing gesture. A result is that the particle empty in an empty universe yields a singularity throughout space-time, bowing toward the only one that exists. Now, we get the fifth step, which is what is going on with many particles now. Let's try to see what is going on in the more realistic configuration. In order to see that, you have a prerequisite before. You have to prove that the gravitational waves, the form momentum of the gravitational waves, they add themselves. So you study a set of n+1 gravitational waves encountering themselves in a given event of space-time, right? Then for each gravitational wave, I from 0 to 1, not to n, you create an infinitely small py particle, virtually, such as its form momentum is exactly the opposite of the gravitational wave form momentum. You can always do that in your mathematical framework. Of course, you can talk about it as being a thought experiment if you like, but it's a mathematical framework of relativity. Then the following equation arises. This first equation is that the form momentum, the resulting form momentum of all the gravitational waves is exactly the opposite from the form momentum of all the particles, P representing all the particles, all the P1 particles. This equation comes from the fact that once we have been doing that, the result is null. We know it because we have been contradicting each cause completely. So therefore, the result is completely contradictory, is null. We know it. So for the full form momentum is null. So the sum of this and the sum of the form momentum of and the form momentum of the particle are null. Therefore, it gives you this equation. And then if you detail what is P, and what is the form momentum of P, this is the usual addition of energy here. this is a definition. The form momentum of Py is exactly the form momentum of the opposite of the form momentum of the gravitational wave, and then you get the result. As usual, it's always the same kind of surfing, except that here it's surfing in the opposite direction. I don't know if you can do this in surfing. Yes, maybe when you prepare yourself to surf, you have to go in the opposite direction. So now, for a countable number of particles, you can have an equation now using the addition rule that we were talking just before. Here, the sum here is not exactly the same as this one. So sorry, this sum here. So here, the sum here is in fact a combination of sets. So you have the mi delta y is one particle. So you have the particle y, which is modelized by the Dirac distribution here. The sum of those Dirac distribution can be done. Okay. Here, what you get here, sorry, it's the sum. There is something with the sum. It's a combination of sets. Okay, I don't have time to go into that. It's quite long. Maybe what can I say? Maybe. Wait, yes. Maybe let's see what is what. This is a particle. Mi delta y is a particle Py. So you get a set of those particles, and you want to know what is the space-time structure, which is obtained by this set of particles. So the rule is that it is the space-time structure of the sum of the limit of the circles. This is the circles we were talking before. For each particle, you have a sequence of circles. For n circles going to you have an infinite number of n circles. You get n to the infinite. Okay, you get the particle, and the result is that you get the sum of the limit. But the limit here of the space-time. So this is the space-time structure of the circle. The limit is of the space-time structure is the singularity represented by a form momentum. And also at the end you get the sum of the form momentum. So that's what is the main result. You get the sum of the form momentum. It can be represented here in the sixth part of the particle. If you get 4 particles here, the final form momentum here in x here. The form momentum is the sum of the form momentum of the gravitational waves. So here n is the number of particles. Here it's not infinite; it's only 4 particles. Here you have your four singular form momentum. Your form momentum which are singular, as I said before. You add them, and then you obtain the form momentum in x. This is exactly this equation. Formulation here. So you obtain in the more general case, when the number is not equal to 4, but whatever it can be, you can go to the infinite also the same way, quite easily with the same behavior of the limit and the space-time structure intervention limit. So you get the form momentum, which is the sum for all the particles of the universe of the form momentum coming from the particles. When I say the form momentum coming from the particle, it's exactly what we were talking about. That is the form momentum coming from the virtual bunch of matters which are inside of each particle. So it's quite weird in physics. It would appear to be very weird, but we are completely in the mathematical framework of relativity without anything strange, in fact. So the space-time structure is given by this equation. You can compare it with the Einstein equation. It will reveal that G is the variable. Of course, you can see also that F, which is F is the attenuation function. It means that when the gravitational wave propagates, the form momentum, the energy of the form momentum here decreases progressively. problem is that we don't know exactly this f function. For calculating it, you need to use a rule which is very profound in relativity, general relativity, which is correct, which is Einstein equation in vacuum, which can be reformulated. The scalar curvature is null. If you use the scalar curvature being null, you can calculate formally, theoretically, the f function, but it's quite cumbersome. But nevertheless, if you assume that the universe is full of matter, in a constant distribution of matter, then you can be assured that this f function will be exactly the same for each particle, assuming that the particles are distributed in a grid, in a regular grid, of course. Homogeneous, everything is homogeneous and regular. So the f function is the same. Then, if f function is the same, it's much more easy, and we exactly retrieve, in fact, we retrieve Einstein equation in that particular case, and then we can compare this equation with Einstein equation. This equation is interesting because it is scalable. It does not use the G constant. Reminder here, Einstein equation is not scalable. It uses the G constant, of course. So now, from it, you can deduce the metric. It is important to know how to do this because general relativity is all constructed around this concept of metric. So this is a reminder here and below. What is new here is this, that now we get the form momentum. In each event of space-time, you can get this form momentum. It looks like this. It's the form momentum of a non-relativistic particle. You can deduce from it the speed. Oh, sorry, yes, I didn't told you that. Here, the singular, I return the singular form momentum here, c mu. We were talking about it many times. It looks like that of course. Huh? It's when time merge with space. For the form momentum is like this. So we get the form momentum in for a non-relativistic form momentum. We get the v speed, which is not equal to c, and then we get the boost in any part of space-time. It is not equal to c because we assume that there are more than 3 particles. There are more than 3 such particles here. So we get away from the monsters we were talking about with the universe completely empty. Okay, we get rid of that. So if you get rid of that, then we get a non-relativistic speed, and then you can deduce the boost here, like this. And then once we have a boost, we can deduce the evolution of the metric between the old GRF and the new GRF. So you have an old metric and the new metric, and the new metric is deduced from the old this way. G of x prime is the new one, the new metric, and G of x is the old metric. I don't have time to go into this tensorial algebra, even though I would be very proud of doing such a thing. Tensorial algebra. The physics is not lying there, so that's why I focus on the geometric description of this demonstration. So now we get the 8th part of the demonstration, which is the prediction of the surrounding effect. So from the fundamental equation we have been finding, we just pass the total energy of d mu from left to right, and then we get this under the assumption that we are in a universe full of particles homogeneously distributed from n equal to 1 to the infinite, and we only consider the particle number of O0 here, and we only consider the deformation generated by this not the zero particle y here, location y0, And then we see that the deformation generated by this Y0 particle is described by V, which is very much identical to the boost. In fact, it identifies the boost that we saw before. This deformation is divided by this sum, which is exactly the total energy of everything else. This is because I took n equals 0 in it, but you can also raise it from the sum. It gets exactly the same result because this sum is huge. In fact, fundamentally, theoretically, this sum is huge. Hopefully, you have the same kind of effect as the old Hilbert effect, so you don't get infinite. It does not diverge. Well, the result is that this sum here is exactly the surrounding energy. This is the surrounding energy around the particle, around X. Yeah, X. So therefore, what you get is that the surrounding effect arises in relativity. What is the surrounding effect? The surrounding effect is that the gravitational force is inversely proportional to the surrounding energy at the location where the force is exerted. So this is the drawing. You have Newton's law, and then you have to add to the equation the surrounding energy here. You put this on the denominator of something which is a ratio, and which acts as a multiplying factor at the right-hand side of Newton's law. So here, this illustration is intended to show that when you increase the surrounding, you restrict freedom. From the physics point of view, it means that when you increase in the surrounding, you decrease elasticity of space-time. The same way, when you decrease surrounding, like for example in a void, when you go in a void, okay, in a void of astrophysics, the surrounding is very low. Surrounding value is very low. The freedom is very high, and the elasticity of space-time is very high, and therefore gravitational force is very much increased with respect to Newton's law. So now we get the final thing, which is the equation of G, which is there is under special circumstances, which are very usual in circumstances. In fact, you get this equation directly from this one, manipulating this 1, 2, 3 times. It's not a big calculation, but it has to be done. Okay. So you have at the end of the story, you have different ways for calculating space-time structure from energy. Either you can use Einstein equation with this new value of G. Maybe it's more practical to use here modelization of the surrounding value, because this one is a divergent sum. It's not practical. It's very much a theoretical equation. And or you can use this Fermi-Monton equation, but it's very much unpractical. As I said before, F is not practical. So the best way is to use Einstein equation with this. In some very simple situations, circumstances, you can use this one also. But the calculation will be a little bit cumbersome. At the end of the story here, this is the end of the demonstration. And now we can see that the possible caveats of the general relativity, which were mentioned above, are all solved. This is all described in my demonstration, which is a 50 pages demonstration available on my blog. Here I remind the address of my blog. It is much more easier to go on Google. Sorry for that. Maybe it's advertising Google or another research tool. You search for a site, Frédéric Lassiaille, my name, Frédéric, and then you get my blog, and then you have to go on the page which is entitled Relativity Predicts a Variability, and the article link is located at the top of the page. It looks like this. So you see, you have a 50 pages article. Okay, so now, what are the consequences? Quickly speaking, because we have been watching that in the previous conferences here in the CNPS. The most direct consequence is in gravitation, of course. We can easily construct a gravitational model which uses this surrounding effect. The most easier way to do is to use a Dor profile with a 15 kiloparsec array sphere for calculating this surrounding value. Then, as I showed you before in January, no, it was in September next. This surrounding gravitational model is working extremely well, and more than that, it gives the explanation why the Monde model was working so well for so long. It gives the explanation. This is surrounding. Now, there is also consequence in particle physics. So this is the final picture now. You see you have relativity in blue. Inside of relativity, you have general relativity and special relativity. You have this Einstein equation, which gives dark matter and dark energy and remaining gravitational mysteries. Okay. Now we have been watching today that there is a mathematical demonstration proving that Einstein equation with a variable g must replace. So I should put a strike on it, but I didn't do that. So I don't want to put a strike on Einstein equation. The result now with this variable g is that we get a gravitational model surrounding, which solves all the gravitational mysteries, and also under a unifying assumption, and we get the solution to the Yang Millennium problem, and also to 2 or 3 old puzzles of nuclear physics. Pardon, sorry. So for more detail about that, please go to the previous CNPS conferences, or please go to my blog. The conclusion, there are 2 kinds of conclusions. First conclusion is about the demonstration of today. The presentation of today shows us that there are new key concepts in relativity to be found, and a new framework to be found, which I called GRF, Generalized Race Frame, which reacts like an absolute spacetime. Relativity predicts a variable gravitational constant. This is shown through mathematical analysis. The general relativity framework, GRF, this is not the correct acronym. GRF means generalized race frame. It's also working for generative framework. Sorry for that. It introduces the concept of absolute spacetime, which is distinct from the SR, but not so different from it in some way. GRF behavior, so generalized race frame behavior, is analyzed by comparing different energy distributions. So we allow ourselves to do so because we are working in maths. So some space-time structure is calculated by a new equation involving the first degree of derivation of the metric. The main results of that are the single particle in an otherwise empty universe leads to a singularity throughout space-time. Also, studying gravitational waves generated by virtual microscopic branches of matter moving at the speed of light are studied. This is done in order to modelize a particle in a universe. By doing so, an equation is derived for such a single particle alone in an empty universe. Then, from this, a generalized equation is given now for a countable number of particles in an empty universe, and so on until, let's say, an infinite number. Infinite is not something physical, so I would say a countable number. A huge number, it's still worse for a huge countable number of particles. Then the surrounding effect emerges naturally in relativity. and the Einstein equation is retrieved when matter density of the universe stays constant, and also when the particles of the universe are assumed to be distributed along the nodes of a regular grid, etc., etc. Everything homogeneous. Then a variable g arises immediately. And an equation for g as a variable is presented. G is not constant, and g evolves according to the surrounding effect. Now, there is also a conclusion from the point of view, if you want, of my whole research connected to all the presentation I've been doing here in the CNPS. So in 3 lines, relativity predicts a variable g, space-time structure is calculated by a new equation, Einstein equation is retrieved when matter density of the universe stays constant. Excuse me. The surrounding effect is a fundamental behavior of relativity. The result, now the consequences in the view of the whole research is that in gravitation, the surrounding gravitational model arises immediately, and the gravitational theories are explained, and in particle physics, as I said, and under relevant unifying assumption. This I didn't say. I talked about that in my first presentation in January. This unifying assumption. Under this unifying assumption in particle physics, many puzzles are explained. In particular, the famous Millennium Young's problem is solved. Thank you for your attention.
Well, thank you very much for that very good and concise talk, something that we've come to expect from you, because you've given all the headlines that you are going to deal with, and then you went through them individually. So thank you very much for that. And I think your talk has actually generated quite a bit of discussion here, which is still coming in. So perhaps before we come to that, maybe just 1 or 2 points, if I may. Well, actually, I was interested in your initial comments indicating that we were moving away from the anthropocentric view of humanity in various ways, and this was a further evolution of that. So that was an interesting part.
Would you like to generalize it to a social context or whatever?
Goodness me! I mean, one could do that, but it did occur to me that I mean there are some flat earthers obviously around, but there are some geocentrists actually. One might consider them to be part of the dissident community. You know, so there is a small minority, and they seem to have made up their mind, but they're giving reasons that on the face of it might appear to be scientific for their concept. But anyway, we're perhaps moving away from that, and
Yes.
So you're perhaps a further evolution in that respect. The generalized rest frame and ether being matter. Now, I just had 1 or 2 points maybe that I might just raise quickly, and then we go to the questions. Could come back if necessary. Could you give maybe an order of magnitude of the variation of G in maybe some typical situations? I mean, is it a small amount, or is it a reasonable percentage of the average value of G?
Yes, of course. You can go more than. Okay, I will talk about the gravitational model, surrounding gravitational model. Okay. For this gravitational model, which has been fitted to experimental data, okay, you cannot go more than 40. So it means that I'm talking about the multiplying factor, which you add on the right side of Newton's law.
A factor of 40.
It means that you cannot go increasing more than 40 the Newton's law. Another way to say it is that in the voids, in astrophysics, you have voids which are completely empty. This is by the way, this is a mystery also. Why the voids are so empty? But in these voids, which are completely empty, the gravitational force calculated by Newton's law must be increased by 40.
So
and then you have no. Sorry. To answer, excuse me. To answer completely to your question, Ian, you have no minimum. Theoretically, you have no minimum, but in fact, in particularly speaking, there is roughly a minimum. It means that when matter goes too dense, it decreases the Newton's law gravitational force. Therefore, it expands the matter by decreasing the gravitational force. It expands the matter.
So this is quite an order of magnitude change. It's not a minuscule correction. Might you put in the same sort of variable g into the Newtonian equation as you might in the Einsteinian general relativity tensor equation? Would you use that with the g factor in and just replace that with the variable g? You know, the big tensor equation with all the...
Oh, yes. Of course, as usual. Not as usual, but because sometimes it's difficult. But you can formulate this classical equation I was showing you. You can formulate it, excuse me, in the general relativity framework. Einstein equation is nothing more than Newton's law formulated in the mathematical framework of general relativity. Am I correct? So the same way, you get this equation of Newton's law modified by surrounding, and you can get also the formulation of it in the framework of relativity. This is something I've been doing. I've been showing quickly this work, the result of this work in a CNPS old presentation. It's available on my article also, many of mine, by the way. Okay, so you can do tensorial algebra calculations in which you formulate this equation in the relativity framework, of course, yes. And it's an exact and it's one and only equation. You don't have different version of this tensorial equation, like as it is the case for Mond, for example. You only have one possible.
So I think some of the questions here, Frédéric, maybe just expand a bit on this. For example, question, well, you may have answered this already, but he says, if G isn't constant, does that mean that it is weaker in some areas of space or something else?
Yes, of course, yes. It varies. So it gets weaker, it gets stronger. Okay. This is for the gravitational model. There is something more to say, which is very strange, if you want. Because you can obtain negative force. You can get negative force, but this is in the weird, not very usual circumstances.
You're not referring to a repelling force. You mean
a repelling force? Yes.
You are. Okay. Yes. Okay. So it can actually move from attraction to repelling in certain cases.
Yes. As far as I remember, it is not for gravitational model sounding. It is really for the work in relativity.
Oh, okay. Question again. He's asked you a few interesting questions. Actually, it's Jerry. But if there is an ether and it has varying densities, that could cause variable G. Well, that seems to be in line with what you've been saying.
Yeah, no. This is interesting. The reason why I don't like to talk about ether, it's not only that I have the feeling to insert history or something, you know. It is this, but not only. The problem is that the absolute space-time we obtain is deduced immediately from matter. The distribution of matter, you have the distribution of matter, and from the shape of the distribution of matter, you get space-time structure. And what I say is that it is space-time structure which is the medium, if you want. So it's not matter. So it's a medium which is not made of matter. That's why, for me, it's not an ether. For me, the ether is made of matter. But there is another thing, which is there is this weird thing about speed of light. You know, speed of light in space-time structure has a special role. And which is not something in common sense, if you want. You have two ways to prove it quickly. You have the first way to understand that the law of physics are the same in every frame. Okay, must be. This is an assumption, of course. So if the law of physics are the same in every frame, then there is a speed for interaction which is the same in every frame. Okay. This is the speed of interaction. When you talk to me, it takes time to go. If it was not the case, we would have serious problem in physics, I imagine. So it takes time. So there is a speed, and this speed is the same for every frame because the laws of physics are the same. Okay? So there is this weird result. And also another argument is simply experimental data. And Michelson-Morley, of course, but another one might be more efficient is also the speed of quarks. The speed of quarks is maybe 99% of the speed of light. Same thing for the electron. So, specifically speaking, we are living in a world in which everything, the real matter we know, is everywhere moving at the speed of light. So that's something with the speed of light.
So you don't accept some recent evidence, which they now say might have been erroneous, that the neutrons were perhaps exceeding the speed of light by a small amount. You do think that's a speed limit?
Yeah, I heard that kind of thing. Maybe it was in 2000 or maybe in 1999. Yes, but it was said, but at the end it was said it was wrong.
Right.
Okay, maybe. In fact, you can imagine that the quarks, for example, I don't know that, but you can imagine that the quarks are made of, inside of them, a small bunch of matter, which are them moving at the speed of light. And in that situation, then it would mean maybe that the real speed of light would not be real c, but would be faster. But there will still be a limit.
Okay. Well, again, we may have dealt with this already, but just questions are coming in. I just want to make sure we're not leaving them out. Robert K is asking, maybe similar to what I said earlier, if perhaps the universal gravitational constant varies, what does it change in proportion to TO, presumably?
Yes, it is inversely proportional to the surrounding energy.
Okay. So
inversely proportional to the surrounding energy.
Okay. This is probably something that you also have dealt with the last time you talked to us.
You have the drawing in my slide if you want to. I can show you the drawing, which is very much explicit.
Do you want me to put something back?
Oh, if you want, if it's possible, but otherwise it's not a problem.
I don't see your screen here.
Okay, maybe maybe I forgot to share.
Yeah, okay.
Well, okay, I can share it here. Arrêter l'écran. Stopping, sharing screen.
And then press it again after you get this image.
Okay, I'll go back. Maybe you can see it.
Yeah, I think I can. Is that it? So, okay, so you're back.
Yes, surrounding. I can find it somewhere here. Yeah, here. Yeah. So maybe you can see it. Can you see it?
Yes.
Oh, so this is the usual old Newton's law, the attracting object and the attracted object, or the attracted location, if you prefer. So the force which attracts this to this is equal to this given by this Newton's law. You can have a minus sign here if you prefer, but so the modification given by relativity in the classical limit inside of the classical system is this one. You must add a multiplying factor, which is this one, which is made of a ratio. On the numerator, you have a constant, and the denominator, you have this surrounding energy. In red, this surrounding energy is really the energy of everything which is around. Let's say in a circle sphere, in a sphere of 15 kiloparsec ray sphere. Yeah, then you get this value, you put it here, and you get this multiplying factor, resulting in the fact that the f is now not the modification of f, that is a g, in fact, g, I'm talking about g, g is increased or decreased by this factor. So it's proportional. It is g is now inversely proportional to the surrounding energy, as I was talking.
You've taken the modified g to be g times constant over surrounding energy.
Yeah, that's it. Yes.
Okay. Well, I think there's probably another question related to that by Robert K. So we'll get it here. Let's see now. Yeah. Well, Professor Hallam Boot. Yeah, he answered again. I think because I did ask, were you applying this to Einstein's tensor formula as well? But Hallam says, did Frédéric try to interpret the variable g? I think he probably means large g in the framework of classical physics instead of framework of Einstein theory of relativity, as he is doing now. So, what success would you have had by restricting yourself to applying this idea to classical physics, Newtonian physics?
Yes, okay. As I told you in the presentation, in fact, the tensorial algebra is not very useful to understand what is going on here. Why? Because the modification which is required is understandable very easily in classical physics. It's exactly what I've been showing you on this slide, in which you add this multiplying factor. Of course, you can have a relativistic formulation of this equation, but the most important thing is here. You just have to take into account the surrounding energy. So in fact, okay, sorry, but this is how we understand it simply. But the reasons for the surrounding mechanism to appear, the reason comes from relativity itself. The demonstration I've been giving to you today is all completely full of general relativity concepts. The boost, the speed relative to the boost, the metric, etc. Demonstration is made by inside of general relativity. Okay. In the core, even more than that, is the real core of general relativity, because we are talking only of the space-time function, the function which gives you space-time structure from energy. This is the core of general relativity.
See, many of us are endeavoring to restrict ourselves to classical physics, or perhaps even resuscitate classical physics with different modifications, and therefore, get the results which I suppose the mainstream would say you cannot be got without general relativity. I think Hallam might be in that category, and I myself could be as well. So that's probably prompted the question.
Okay, okay. Maybe
yeah,
I
but if
understood
I
more.
may just come
Okay.
to another related, it's actually addressed to Jerry, but Jim Morrison is suggesting, I think, that the variations in ether density, which you talk about, would be equivalent to variation of gravitational potential, which results in a gravitational force. So he says rather than a change in G, he's looking at it in terms of that. Is that an alternative way?
Yes,
your way, or
yes,
is it
exactly. Yeah,
contradictory?
absolutely. Yes, yes, this is
Okay.
correct.
Okay.
This is okay. You have obviously maybe I didn't point that too much. Okay, I should have pointed that more. You have different way. Not only this one, also you have maybe 3 or 4 way different way of formulating exactly the same mechanism which gives the same result. Either you talk about a different G, or you talk about a different potential, yes. Or also, I have been hearing about increasing the mass also, or increasing the energy. Yes, this is something in which energy will not be constant. You see, so okay, it might appear weird for somebody who has been working on physics for long ago, so, violating the energy conservation principle. But you can imagine that okay, energy is not conserved, and then and the mass is not conserved, and it increases with depending. This is more maybe more relevant than the energy. Is to consider that when you have an energy, it's always relative to another. That is really correct. This is another way to see, which gives exactly the same result, and which is relevant also. Except that when you go in full detail, when you want to have equations which are compatible with the old mainstream equation, because you want to compare, okay, it's difficult. But nevertheless, it's very relevant. You can say this. You can say that when you have a mass, for example, one man alone in a desert, he's got a mass which is bigger than when this man is inside of a riot or many people.
Right, a crowd. Yes, okay, molecules. Well, just getting back to this again, if more fundamentally, I suppose. I don't know if he understands everything, but he's saying, Robert, if K varied, then the gravitational force would vary. F is, I suppose, of the order of G over R squared, such that the force would be constant. The force is currently measured to be F, varying as the square, inversely as the square of the distance. We do not measure a variable G. So I'm not quite sure what unfortunately, he's not in the green room. I'm not quite sure what he's saying.
No, I think maybe I understood. Because there are 2 variations. There is a variation of G, and there is also the variations of Newton's law. So it may be confusing. So that's the thing I understand in this sentence. Maybe I'm wrong.
He might be saying, look, you can encapsulate all these variations in the law as is. You don't have to vary G itself. And he seemed to be saying, I'm interpreting it probably incorrectly. He's saying, well, look, if G varied, it might cancel out any variation owing to distance. And
Okay. So please let me show you the slide here. Can you see it?
The slide.
Can you see it?
Yes.
Yeah, you have the variation here of the green arrow. If the green arrow decreases, if the surrounding energy stay constant, you get Newton's law. In fact, except that it's a G, another G, but it's Newton's law. But now, if you stay this green distance equal constant, then you can vary also the surrounding energy. Then you get another variation of F, which is coming from this new factor here, this new term. So you got many ways of modifying F, which are not contradictable. They do not contradict themselves. They are just acting on different data. They are causes, but completely different reasons. causes.
Okay. Well, we might have a little time just to discuss this in a bit more detail, because well, just before we do that, I'll just maybe put a basic question of Jim's up again, Jim Morrison, because he says, are there any experiments to test this theory? Now, I'm wondering,
Yes.
are you talking a bit more about those on your blog, by the way, Frédéric?
Not so much, because I've been writing articles about experiments, but I'm quite ashamed there was small mistakes in these articles, so therefore I don't publish them too much. Of course, there are very interesting experiments to test this theory. The most important one is about the measurement of G. So it consists of measuring the gravitational constant G in a laboratory 2 times. The first time, as usual, and another time, the same exact measurement, except that you put the attracting object inside of a shield. You protect it with a shield, a metal shield, assuming or expecting that by doing so, the gravitational constant will decrease because of the shielding of the surrounding effect.
Yeah, sorry, I'm just having difficulty getting the photographs up. We're both on, but I cannot get the photographs up.
Maybe
yeah.
I can stop my sharing. Maybe that's why.
It might be, yeah, it might be you. That if you stop that.
Yes, I stopped. I have been stopping that. Yes,
but it's still not coming up.
I no longer share. I no longer share.
Very odd. Very odd. Videos seem to be. Wait a minute now. Maybe I'll try that. Yeah, I don't understand that. It just disappeared when you stopped sharing. I couldn't get the photographs back. It doesn't seem to be giving me any.
Maybe I can do the modification again. I share and then I quit the sharing.
Quit it.
I try.
I can add. Wait a minute. I'm not able to add it.
Yes.
Yeah. Okay. Yes. We're getting it.
I've been circumventing the bug. There was a bug.
I've put Jim Keen up there, and we probably will talk to him in a moment. So maybe that I just okay. So and I just want the format of that because we don't have any screens at the moment. That's it. In fact, we could probably do that. Yeah, do it this way. Okay. Well, I don't know. We may come to this in the discussion, but I suspect that you are taking also some of the well-known experiments that we talk about. I mean, you mentioned Michelson-Morley earlier, and you're perhaps interpreting them to be consistent with your ideas of a variable G, whereas there are many other explanations for the sort of results they got. So we can multiple that. With regard to the green room people, so some people have disappeared. They came in at the beginning. I think Vladimir has gone, but anybody want to talk? Well, you see, Jim Keen has been putting a number of comments up here, and let me see. Can I just get them down for my own reminder? In the private chat, so people won't actually see those. And as usual, I'd like Jim to express them in his own eloquent way. So, Jim, with regard to some of the questions you've asked, and also we'd like your feedback on this whole question. Would you like to put any of these points to Frédéric and maybe give your own take on his whole concept of a variable G and how it fits in with maybe some of your ideas?
Well, if the so-called constant capital G is variable, as Frédéric advocates, that sort of blows out of the water the Planck scale, because G is used to define the values in the Planck scale. And so it would mean that those values would also be variable. That's just a little comment. I wanted to ask Frédéric, what is the proton radius puzzle? That was on one of his last slides.
Yeah. It's a very old puzzle, which is that when you get a proton made of yes, you get a proton, so it's made of quarks, and you got a proton with an electron, and you've got also you can also create a proton with you can replace the electron by another how we call it, muon, which is heavier. I don't remember if it's heavier or lighter than the electron, but you can replace. Heavier? Okay. Well, yes, probably yes, because it's another next step of generation of particle. Okay, and then you get another atom, and then if you do collisions with other things, I don't know what is a thing which is put on it. Then you calculate a different cross section. And by calculating this cross section, you deduce what is called the radius puzzle. The proton radius. Sorry, excuse me. The proton radius, in fact, it is a cross section. The cross section you obtain when you how we say, you fire with some particle. You fire the proton with one electron, and then after that, the day after, you fire the same proton with no electron but a muon. Okay.
So what you're calling a puzzle is
the puzzle is that it change. The cross section is varying, but it should not be varying.
Why should it not be varying?
It's what is predicted by today's physics.
I don't know why it should be varying. It seems you are simply saying that with different methods, you get a different estimate of proton radius. Current estimates in the literature are in the order of magnitude of 1 femtometer, a little bit more or a little bit less, depending, again, on the method used to measure or estimate that value. Okay, a second question is, what is the AY puzzle? That was just in your slide also, just above the proton radius.
No. Okay, so this was a mistake. Sorry. It exists, but AY? It's not explained. It's not explained. The AY puzzle exists. I don't remember the full story, but it is not explained easily by my work. And sorry about the proton radius puzzle. I don't remember the full details. Sorry. Just it was very vague what I told you. It's not precise enough. Sorry for that. But when I was working on it, it appears to me obvious. But okay.
Yeah, I just don't recollect that. When you say Y, is it the letter Y or WHY?
AY. No, it's like it is written. A and A is like
something.
Yeah, I have to read it to write.
In the slide, it was capital A, lowercase y.
Okay.
Yeah, what Frédéric just posted. Yeah, I was just curious what that was. Well, thank you very much.
So, thank you for your remarks are very interesting. Thank you.
Oh, yeah, AY puzzle. Yeah, I got it here. Oh, okay. Well, thank you, Jim. Have we dealt with all the questions you asked? You were talking.
Oh yes, maybe I can answer something interesting to you. Also, James Keane, because one of the interesting experiments is, as I said, measuring the gravitational value G. Like the Cavendish experiment, as I said, okay? Do you understand?
The Cavendish experiment.
Cavendish, right? This one experiment, but 2 times. You make the two times experiments. One with a shield and one without shield. And also, there is another experiment which is interesting, which is measuring
what
a
happened
possible.
with the one? What?
A poss-
Excuse me, sir. What happened with the one with the shield? I think you said so, but I don't recall. What was G found to be weaker with the shield?
I don't know. I think I don't know. As far as I know, this was not tested before. As far as I know, I don't know.
Oh, so that was a thought experiment. That was somebody
Yes,
actually.
it's an idea. It's an idea I have for an experiment to do it, and there is a prediction of my research for this experiment, of course. So it would be interesting to test and to see if my predictions are correct or not. And the second one is about the H value, the H value, which is
Planck's
E
constant.
equal to H mu, Planck constant. Yes, Planck constant value. I'm not talking about the Planck scale. You were talking about Planck scale.
Yeah,
Now I'm talking about the Planck value. The Planck value, it's a constant also, and it should vary also. Understanding my research further as being a unifying theory. Okay. So therefore, there is an interesting experiment we could do in order to measure a variation of the Planck constant. This could be possible maybe with the new interferometer we have today, which are very precise. This is interesting. So.
Well, in my work, the Planck constant depends upon the alpha coupling constant, and that alpha coupling constant depends upon energy density of the environment in which it's measured. So my work suggests that Planck's action constant H is would also vary depending upon the energy density, again, of the system in which it is measured.
Is it a regular mainstream result or your work? Is it your work? Is it from your work?
Yes. Well, there are books and there's a website, binarymechanics.blogspot.com is my own online journal. Or you can just Google binary mechanics. And you'll get all of that information on the constants.
You two gentlemen.
I'll write it on paper, okay.
But a conception I think might be that where we have general laws that have been in existence, and we find that some of the so-called constants in those laws are actually not really constants. For example, I was thinking of you have certain thermodynamic principles where you have maybe cooling or something like that, and if you give it sort of an exponential decay of the cooling, and you find that there's a time constant in that, and you find that time constant actually isn't constant; it's a variable. Well, you can approximate the law of cooling by a quasi exponential law with a variable time constant, but actually physically that would indicate that the fundamental law is actually not exponential. It's a modification of that. So and it's quite it's quite significant the orders of magnitude of the variation. They're not like just slight modifications. They're quite significant. You said earlier that you could even get repulsion in extreme cases. So I think it might be useful if we had some figures, I suppose a rehearsal maybe of some of these experiments. Maybe you've done this already on your blog. I don't know. Some of these experiments, maybe well-known experiments for all I know, maybe Cavendish experiments, maybe other ones. And we had the results of maybe assuming the sort of basic laws that we have been assuming, and maybe the modification that you're putting in, and maybe the differences. That might be useful, perhaps, certainly in comparing with other ideas such as Jim's work, or maybe my own for that matter, because I've looked at some of these matters, and I haven't noticed maybe a necessity to make such great changes in orders of magnitude. But
Okay,
just to
maybe.
remind us, and I've asked you this probably countless times before, Frédéric, to get any information that you have on your blog, do we just Google Frédéric Lassiaille or something?
Yeah, that's it. Yeah.
And that'll get it for us. Yeah, I
Yes,
did
yeah.
that before, but I did it a couple of months ago. So Jim, it might be worth having a look insofar as there's any contradiction with your own work, or maybe complementarity, for all I know.
Well, my purpose today is not really to talk about my own work. It's our star of the day is Frédéric. I had a couple more questions here. Just a comment with regard to vocabulary, that you use the term non-relativistic particle, and that usually refers to something with a low velocity, not one up at c, the light speed c. So that's just a terminological
Yes, I changed my
comment.
using. Yeah,
The other question I had, or another one,
excuse me. Yes. Yes.
in other words, what you're talking about would be called relativistic velocities, not non-relativistic velocities, because you're talking about a particle going at moving at a velocity c. Now, I wonder why you chose that velocity, because many physicists would wonder what would then be the mass of a particle. Would it have infinite mass, or what? Why you chose that a particle could even move at velocity c in the first place?
But
Even with accelerators.
Okay, because it exists.
Go ahead. Sorry.
It exists already. You have the photon. Okay, I realized that I made a mistake. Okay, you're right. When I want at one slide, I talked about a non-relativistic speed. I wanted to say a speed which is not equal to c. I wanted to say that. Yes. But
You see, the photon is not something which has been necessarily demonstrated as an existing particle. It's just a word that people use to say, well, it moves at velocity c, and so therefore its mass must be zero, and so forth and so on. I mean, it's not something that actually exists physically as a particle per se.
Oh yeah. Okay.
In my opinion.
Yeah. Okay.
Okay. I think
this is a good remark.
Why you're using the c velocity.
It's not. In fact, it's not a problem.
Or why not use half of c?
For my research, it's not a problem because my research is only mathematical. So you are in the model of which is a mathematical model of relativity, and you can imagine everything you want in order to study the S function, what I call the S function, which is giving you the space-time structure of energy. You can imagine everything you want.
Okay, could we leave it at that, Jim, unless you have any very quick point, because we're running out of time.
Oh, yes, and thank you, Frédéric, for joining us again.
And thank you for your contribution. Now,
thank you very much.
Okay, right.
I try to go on this blog. Okay.
No, okay. I see Harry Ricker has logged in. I thought he had a question to ask, but you're coming in and out. Harry. There's an echo, Harry.
I'm having some problems setting up. I'm sorry. I don't really have any questions. I'm just listening in.
Okay.
But I do have one remark, which is that I'm not really sure what you mean by variable G. Variable with time or variable position in space?
Yes.
A variable.
Two of them. Yes, the two of them.
Okay, so that might be clearer if you pointed that out in your at the beginning. I didn't really quite understand that part.
Okay, good.
Variable with time would be interesting because then G would vary as the universe expands, I would think.
Yes.
The energy density.
Well, if you believe in,
That's why. Yes, that's why you're playing an edge of your universe to 100 gigahertz. That's why.
That's why.
Okay. I've just tried muting Harry's mic, so when we're talking, we don't get the echo back through his system. But yeah.
And also, there is what many guys, several guys who are working in the mainstream science, let's say, about a possible retardation of gravitational interaction. It's badly noted by mainstream because it's not official physics, Official physics tells you that the gravitational interaction is immediate interaction. Okay, so my research work shows that it's retarded, of course. It's made of gravitational waves. And those people who are working in this.
I better mute again. So you're talking about retarding at the speed of light. Yes. It's like an R over C thing. Yeah.
Yes. And those people with this work, telling that interaction is moving at the speed of light. They have interesting results in cosmology. Slight variations of quantum. This is also another effect of my new chapter of Relativity.
Okay. Well, this is another subject that it might be useful to come back to at a later stage. The whole question of gravitational interaction and gravitational waves, which you did talk about. That's really another aspect, but we really don't have time, I suppose, to go into that very much today because we're running out of time. So, Harry, before we leave you and the slight audio problems you have, is that all for the moment?
Well, I have another question. I'm not sure. I'm not sure how the gravitational constant enters into the field equations, and I'm not sure. It would be a little bit easier for me to understand if you explain how the G is constant in Einstein's gravitational equations, in those tensor equations. I don't understand, is G separate from the bending of space and time, or is it somehow influenced by the space and time bending?
No, it's the
first sentence.
The first sentence
is correct.
G,
okay,
G is used for
I was unclear about that, and so I think people I don't really know that much about general relativity. To me, it's confusing because you got all these equations, and then the equations are really simplifications of these giant matrices, and it's hard for me to understand what's going on inside of all these components, these IJ components that they have.
That's why I was a little bit.
How we say?
Not despising, but almost in front of tensorial equations, because those things are like Kabbalistic things, which makes the mainstream science in their own tower, tower of glass,
Yeah. But apart from conceding, Frédéric, that the same principles that you've enunciated could be applied to the tensor equation of general relativity, you introduced it in terms of special relativity. That's how you started.
Yes. Why? Because I was searching for an equation dealing with the first metric derivative, the derivative of the first metric. What does it mean in general relativity? This means restricted relativity. restricted relativity with the famous Lorentz transform is exactly the first degree of derivation.
Okay, but at that stage, you weren't talking about things like Schwarzschild, metrics. You were restricting yourself to the special case with non-gravitational forces. To substantiate your contention that one had to impose a variation in G to get the correct results. So, as I say, it'd be useful maybe to get a little table at some stage of
Yes.
of some of the results and contrast them with what would happen if you kept G constant in those extreme cases. That would be interesting. Yeah. Okay.
Yes. In fact, Jan, this table is close to the table, maybe, as far as understood, maybe. Close, but not exactly the one. Close to the table I've been showing in my last presentation about surrounding. You know, when I presented the gravitational mysteries with lines, one line for each gravitational mystery, and then the columns were dark matter, lambda CDM, and monde and surrounding. And
I remember that, yes.
We went to see the differences. Also, I didn't write the first column, which would be Newton's law or general relativity with Newton's law, which would be the first, and in which case this column will be full of ruled out, of course, because we are talking only about gravitational mysteries. Okay.
Okay. Well, I just come back to my own prejudice, if you like, that if so-called constants in fundamental physical equations, mathematical equations representing physical phenomena, are actually not constant, and I'm not convinced of this, but if they are, well, then the fundamental laws are not actually correct. They need to be modified. But so that's just maybe a way of looking at things. But we're coming to the end. I think we're going to have to summarize, and I'd like to give you time, Frédéric, to give us a couple of minutes of your take on today's talk. I mean, after your other 3 talks, I think you've now given us this one, and we did request it. So thank you very much for being quantitative with regard to this aspect. And I think it would be useful, actually, for some of us who are now maybe looking at this again, to go back to your previous the previous lecture, as you say, on surrounding. It's on the YouTube channel of the CNPS, of course, and maybe look into this in more detail. And we may have our own private discussions on this during Harry's cosmology sessions, for example, on Sundays. We may have a brief review of this. A few more comments are coming in, but they're very sort of long discussion ones from Cerna and Shockwave. We need more specific questions if you want to have them dealt with. So forgive me for that. So we've had an interesting discussion. Not too many people in the green room today, but we've had an interesting discussion and a number of fundamental questions, which I hope. Jim actually seems to concur with my idea about the modifying the laws. So I hope it's been useful to you, Frédéric, our comments and our positive and
yes, of course, yeah.
constructive criticism and so on. So I'm going to give you the floor for as long as you want, some minutes, to add to anything that you've said over the last hour, and even during the questions as well, and maybe summarize very briefly where we are today, and maybe indicate how we might go and supplement some of the work with some further work. So for as long as you want, another number of minutes, I'm going to leave and give the floor to you, Frédéric.
Yes, once again, thank you very much for giving me the opportunity to present this work today, for having given me this opportunity. So this presentation was about the mathematical framework of relativity. I demonstrate that G is a variable, and I give an equation for calculating it, and I show that there is a surrounding effect in relativity, which gets, and then this is the presentation. This was the presentation of today. Then you can see on my previous presentation that this has important consequences in gravitation and also in particle physics. Now I would like to I am looking forward to any kind of collaborations. For example, there was the question of James Keane here, which is for me very interesting, extremely interesting, which is that maybe alpha would depend on the surrounding energy. This is extremely interesting. It would be very important to go in such a work as well, which is in conjunction with very much in complement in conjunction, which is very much inside the work I'm doing. And the same way, everybody would be very welcome to join me in this research, because I have too many work to do. It's a huge work. I have work to do in surrounding, work to do in particle physics, in nuclear physics. As you saw today, I don't know very much enough about particle physics. In fact, so I don't have the time to look at everything, which are the consequences of this discovery. Okay, so thank you very much once again, and I will try maybe to show the possible experimentation, the possible test, validation test or validation experiment on another occasion, on another presentation possibly. Thank you very much once again to everybody, and you're welcome.
Well, our thanks are certainly due to you, Frédéric, for having gone to the trouble of explaining all these complex matters to us, and your work over a long period of time in an audible way, a visual way, and answering those questions. And in fact, thank you also for your patience in agreeing maybe to look at the possibility of supplementing some of the information you've given on this and previous occasions. A lot of information there, with some of the tabular data as to what this might change if we did take a G varying in space, for example, and so on and so forth. So what you said just now actually was something that was occurring in my mind, because we'd be interested to see how you progress in some of these matters in your own work and in some of the ideas, perhaps, which we hope have spurred some of that further work from today's questions. And if you'd like, do keep in touch with us. Please continue to participate, and we hope to hear from you. But if you'd like to consider maybe come next year, early next year or something, keep in touch with us. And if you feel by then that you've progressed in some of these areas, you could perhaps give us a talk. We'd be very grateful for that. We're full up now to the end of the year, but I mean, we're very close to the end of the year, and early next year we could look to see whether we could fill in some slots in the program. So thank you very much for that. And I might say we didn't have any problem in absorbing all the time available, despite the fact that I think we only had 2 continuous people in the green room. So there's a lot of information there. And if anything, regrettably, one had to cut off the aspect which you yourself raised towards the end, Frédéric, about the retardation of the gravitational effect. That's a subject in itself, and I'd like to deal with that in more detail. Maybe if you do come back to us and talk about some of these disparity results in experiments where you take a constant G vis-a-vis a variable G, we might come back to this question of gravitational interaction on gravitational waves. So I must finish the session now. We've come up to the 2-hour session, and I'd like to thank all of you for participating, all of your questions. Sorry if we didn't have the opportunity of dealing with every single one. As I say, we ran out of time, and we tried to deal with the more specific questions addressed with regard to today's talk. I know some of you were talking generally around that, and that's to be welcomed. We've no problem with that, but we couldn't deal with all those points. And thank you very much for, in particular, Jim and Harry for coming back on the green room and helping us with the discussion. But last but not least, of course, Frédéric, for having given us another marathon session on his work, and for giving us all the results in very, very clear PowerPoint slides, and dealing with the questions which were coming in. Billy, I see there are 10 more comments that have just come in since I took the floor now. We don't have time to deal with those. But thank you very much, Frédéric. It is much appreciated. And this is a record which is available now for all of you to look at in the recording. And perhaps just do a Google search for Frédéric's blog if you want more information. So I'm going to end the stream now, and thank you all very much for your time, in particular Frédéric, for giving us the benefit of his long research and explained to us very clearly. So thank you all for participating. Good day.